What problem does RecurrentGemma2b aim to solve, compared to existing models like Gemma 2b?
RecurrentGemma2b aims to solve the issue of memory efficiency and inference speed on long sequences compared to existing models like Gemma 2b. While transformers like Gemma 2b require a KV cache that grows linearly with sequence length, leading to increased memory usage and reduced efficiency, RecurrentGemma2b compresses input sequences into a fixed-size state without sacrificing performance. This reduction in memory use allows RecurrentGemma2b to perform efficient inference on long sequences, as its state size remains bounded and does not increase with longer sequences beyond the local attention window size of 2K tokens. This advantage enables RecurrentGemma2b to generate sequences of arbitrary length more efficiently than models like Gemma 2b, especially in tasks where inference speed and memory efficiency are crucial.
How does the proposed method of RecurrentGemma2b work? Provide a step-by-step illustration.
RecurrentGemma2b works by compressing input sequences into a fixed-size state without sacrificing performance, reducing memory use, and enabling efficient inference on long sequences. The model is based on the Griffin architecture, which utilizes a mixture of linear recurrences and local attention instead of global attention. The input embeddings are multiplied by a constant equal to the square root of the model width, and the input and output embeddings are tied. During training, weight decay is not applied to the parameters of the recurrent layers, and the derivative is clipped to a maximum value of 1000 for stability when backpropagating through the square root operation in the recurrent layers. The model is pre-trained on 2T tokens, using a large general data mixture followed by training on a smaller, higher quality dataset. A subset of the sentence-piece tokenizer with a vocabulary size of 256K tokens is used. The model undergoes instruction tuning using a novel RLHF algorithm to fine-tune it to output responses with high reward following a specific dialog format. RecurrentGemma2b achieves comparable performance to Gemma 2b on downstream evaluations, even though Gemma 2b was trained on 50% more tokens. The model's smaller state size compared to transformers allows it to generate sequences of arbitrary length efficiently, with higher throughput at all sequence lengths considered compared to Gemma.
What are the theoretical and practical benefits of using RecurrentGemma2b over traditional transformer models like Gemma 2b?
The theoretical benefits of using RecurrentGemma2b over traditional transformer models like Gemma 2b include the ability of RecurrentGemma2b to compress input sequences into a fixed-size state without sacrificing performance. This feature reduces memory usage and enables efficient inference on long sequences. Unlike transformers, RecurrentGemma2b's state size remains bounded and does not increase with longer sequences, allowing it to generate sequences of arbitrary length efficiently. Additionally, RecurrentGemma2b achieves substantially faster inference speeds compared to Gemma 2b, as shown in throughput benchmarks where RecurrentGemma2b consistently outperforms Gemma 2b at all sequence lengths considered. Practically, RecurrentGemma2b's reduced memory requirement allows for larger batch sizes during inference, which helps amortize the cost of loading model parameters from host memory into device memory. This advantage leads to more efficient inference, especially on long sequences, where traditional transformers like Gemma 2b may face limitations due to the growing KV cache with sequence length. Furthermore, RecurrentGemma2b's specialized Pallas kernel for TPUs enhances its performance during linear recurrence operations, contributing to its overall efficiency in processing tasks. Overall, the combination of faster inference speeds, reduced memory usage, and efficient processing on long sequences make RecurrentGemma 2B a practical and effective alternative to traditional transformer models like Gemma 2B.
How is the training process of RecurrentGemma 2B described in the paper?
The training process of RecurrentGemma 2B is described in the paper as follows. The model is pre-trained on sequences of 8,192 tokens, using a dataset similar to Gemma 2B, which includes English data from web documents, mathematics, and code. The pre-training data is filtered to remove unwanted or unsafe utterances, personal or sensitive data, and all evaluation sets. RecurrentGemma 2B is pre-trained on 2T tokens, unlike Gemma 2B, which was pre-trained on 3T tokens. The training starts with a large general data mixture and continues on a smaller, higher-quality dataset. A subset of the sentence-piece tokenizer with a vocabulary size of 256K tokens is used, leading to a significant fraction of the total model parameters being in the embedding layer. Additionally, the paper mentions an instruction tuning approach similar to Gemma, involving a novel RLHF algorithm to fine-tune the model for high-reward responses. The instruction-tuned model is trained to follow a specific dialogue format. The training process also includes evaluation across various domains using automated benchmarks and human evaluation, showcasing the model's performance against Mistral 7BV0 to instruct model in different tasks.
What specific results were achieved by RecurrentGemma 2B in terms of performance and efficiency compared to Gemma 2B?
RecurrentGemma 2B achieved substantially faster inference compared to Gemma 2B. It was able to generate sequences of arbitrary length efficiently due to its smaller state size, which did not increase on sequences longer than the local attention window size of 2K tokens. This efficiency was demonstrated in throughput benchmarks, where RecurrentGemma achieved higher throughput at all sequence lengths considered, with a maximum of 6K tokens per second during sampling, while Gemma was substantially slower. Additionally, RecurrentGemma's reduced memory requirement allowed for larger batch sizes during inference, which further improved efficiency by amortizing the cost of loading model parameters from host memory into device memory. These results indicate that RecurrentGemma 2B outperformed Gemma 2B in terms of both performance and efficiency during inference tasks.
What are the limitations or drawbacks mentioned for the RecurrentGemma 2B method in the paper?
The limitations or drawbacks mentioned for the RecurrentGemma 2B method in the paper include the fact that the throughput achieved by RecurrentGemma when sampling as 6K tokens per second, which is slower compared to processing input prompts where both Gemma and RecurrentGemma achieve a throughput of roughly 40K tokens per second. Additionally, the paper notes that users should expect lower throughput when using the PyTorch implementation or when using GPUs. Another drawback mentioned is that sampling will dominate the total time required unless the prompt is significantly longer than the desired sample. Furthermore, the paper highlights that the reduced memory requirement of RecurrentGemma enables it to perform inference at larger batch sizes, which helps amortize the cost of loading model parameters from host memory into device memory.
What future work suggestions are made by the authors regarding RecurrentGemma 2B?
The authors suggest future work for RecurrentGemma 2B, including exploring larger model sizes and training on more diverse datasets to potentially improve performance further. They also mention investigating different tokenization strategies to optimize model parameters and efficiency. Additionally, the authors propose studying the impact of different hyperparameters on model training and performance. Furthermore, they suggest exploring ways to enhance the instruction tuning process and potentially developing new algorithms for fine-tuning models for specific tasks. Lastly, the authors recommend conducting more extensive human evaluations across various domains to assess the model's capabilities comprehensively.
What modifications were made to the Griffin architecture to create RecurrentGemma-2B?
To create RecurrentGemma-2B, a single modification was made to the Griffin architecture. The modification involved multiplying the input embeddings by a constant equal to the square root of the model width. This adjustment was implemented to enhance the model's performance. Additionally, the input and output embeddings were tied together, but the multiplicative factor was not applied to the output embeddings. This modification is in line with the architecture of Gemma, which also incorporates a similar multiplicative factor. The key model hyperparameters were defined in a table, and it was noted that weight decay was not applied to the parameters of the recurrent layers during training. Furthermore, to ensure stability during backpropagation through the square root operation in the recurrent layers, the derivative was always clipped to a maximum value of 1000.
How was the evaluation of RecurrentGemma-2B conducted according to the paper?
The evaluation of RecurrentGemma-2B was conducted across a broad range of domains using a combination of automated benchmarks and human evaluation. In terms of automated benchmarks, the performance of RecurrentGemma-2B was reported on various downstream evaluations, showcasing comparable performance to Gemma 2B despite being trained on fewer tokens. For human evaluation, the final instruction-tuned model, RecurrentGemma-2B was subjected to human evaluation studies against the Mistral 7BV0. To instruct model. The evaluation involved around 1,000 prompts focused on asking models to follow instructions in creative writing and coding tasks, where RecurrentGemma-2B achieved a 43.7% win rate against Mistral 7B. Additionally, around 400 prompts were used to test basic safety protocols, resulting in RecurrentGemma-2B achieving a 59.8% win rate against Mistral 7BV0. To instruct model. These evaluations demonstrate the model's performance and capabilities in various tasks and scenarios, highlighting its effectiveness and competitiveness in the field.
How does RecurrentGemma-2B's state size advantage contribute to its faster inference speed as compared to transformer models like Gemma?
RecurrentGemma-2B's state size advantage contributes to its faster inference speed compared to transformer models like Gemma by having a bounded state size that does not increase on sequences longer than the local attention window size of 2K tokens. This means that RecurrentGemma does not need to continually grow its state like transformers do with their KV cache, which grows linearly with sequence length. As a result, RecurrentGemma can efficiently generate sequences of arbitrary length without being limited by memory constraints. This reduced memory requirement allows RecurrentGemma to perform inference at larger batch sizes, which helps amortize the cost of loading model parameters from host memory into device memory. Additionally, RecurrentGemma's smaller state size enables it to achieve higher throughput at all sequence lengths considered, as shown in throughput benchmarks. This advantage is particularly evident during sampling, where RecurrentGemma achieves a throughput of 6K tokens per second, significantly faster than Gemma.